My name is Michael Hotard. I'm a student in Math 23A, and I'm going to show the proof for our class 6.3. It's all about Cauchy sequences. And I don't have a whiteboard today, so I'm going to try to write this out on paper and try to hold the camera in a way that it shows what's going on. So we're going to start with prove that any Cauchy sequence is bounded. So we know that for all epsilon greater than 0, there exists some n such that nm greater than n implies that s sub n minus s sub n is less than epsilon. So we're going to start off with our Sn, and we're just going to add 0 in the form of Sn and Sm and minus Sm. So we're going to do Sn minus Sm plus Sm. By the triangle inequality, we can split this up and say Sn minus Sm plus Sm is less than. So now we're going to exploit the fact that we know this is Cauchy, and so we know that for some n, nm greater than n, the following holds, that Sn minus Sm is less than an epsilon. We can pick any positive epsilon, so let's just go ahead and set it to 1, keep it simple, and let's just assign our m to n plus 1. We can do this, it's greater than n. So we have Sn minus Sn plus 1 is less than 1. So actually now we're going to do this substitution. We're going to substitute this 1 up to this equation up here. So here we had Sn was less than or equal to now 1 plus Sm. But we actually defined our Sm, so we have less than or equal to 1 plus Sn plus 1. Look, it's bounded! Hooray! For n greater than n. And we also know that actually this should be a definite inequality, and then this is this. We know that it's max of S1, S2, dot dot dot, all the way to Sn. So it is bounded for n greater than n and for n less than or equal to n. So that's part 1. Part 2, show that any convergent sequence is Cauchy. So we know for a convergent sequence that Sn minus S is less than epsilon for some n greater than n. And then epsilon, of course, is greater than 0. So we're going to start off by starting off with what we want to show. And again, we're going to add 0 to both sides in the form of plus s minus s. And then we're going to split this apart using our handy-dandy triangle inequality. Because there is some n such that n greater than n, this is, we can set this to anything because this property holds. So we can set this to less than epsilon over 2 plus epsilon over 2. And so we get less than epsilon. So we have shown that this convergent sequence is a Cauchy sequence for nm greater than n. So that's what we have so far. And now comes an interesting point. We're going to do this a little differently than we did in class. We're going to use the Bolzano-Weierstrass theorem to show that any Cauchy sequence is convergent. So we've shown that our Cauchy sequence is bounded in the first part, and so we know that any bounded sequence has a convergent subsequence, and that is the Bolzano-Weierstrass theory. So that we know that there is some subsequence, S and K, for which this is less than epsilon. Because it's a Cauchy sequence, we also know that Sn minus Sm is less than epsilon. So we're actually going to, and what we're trying to show, that Sn minus S. So we're going to say that Sn minus Smk plus Smk minus S, we're adding 0, and we know that this is less than or equal to, by the triangle inequality again, Snk minus Smk plus Smk minus S. This kind of looks like what we have up here. So we know by Cauchy that there's some n such that this is less than epsilon over 2, and we know by BW that for some n, this is also less than epsilon over 2. So now we have less than epsilon. So we show that for a Cauchy sequence, there is some n such that n and m greater than that n imply that Sn minus s is less than epsilon, and therefore any Cauchy sequence is convergent.